Greetings, calculus adventurers. I would like to talk with you today about a technique in integration called u-substitution. It's what I think of as undoing the chain rule. So remember that integration is the opposite of differentiation, and our goal is to find an antiderivative. That is to say, a function where when I take the derivative, I get the integrand. The integrand is the function that I am integrating, so it's the thing behind the integral sign before the dx. Dx is the differential. And we want to find a function so that when I take the derivative of it, I get the thing inside of here. So I want you to observe that I've got a composition of functions written here, so that I've got some function of g, and then I've got a derivative that appears outside of it. And this is exactly the scenario that we try to apply the technique of u-substitution to. Like, so for example, we might be integrating e to the sine of x cosine of x dx. So I've got a composition of functions right here. So g of x is the interior function. Look, so I've got sine and I've got the derivative of it. Here's g prime. The derivative of sine is cosine. So I've got f of, and then I've got this g pair. And our mission is to try to figure out, when approached with one of these problems right here, like which thing is f, which thing is g, and then to set up the problem using terminology that puts you on the right path. However, I've been calling it g, and the technique is called u-substitution. And so I'm going to replace g here, which I wanted to start with because I figured that maybe you were more comfortable with g instead of u. I don't know. So I'm going to put my u in here, and now it looks like the pattern for u-substitution. So we're going to try to find the outermost function here that looks different from the rest. I'm looking for inside the function that I'm going to integrate some sort of like derivative, function derivative pair. So I've got like sine, cosine going on right here. So I'm going to try to like be like, okay, so like if that thing is u, if like sine is u, then what's the outer function? And then I'm going to like try to rewrite the thing, and it might take you a couple of tries to do this. So I'm going to get it right on the first try because I have been talking through it already. So I'm going to let sine of x be equal to u so that this thing looks like e to the u. And then I'm going to consume this whole expression right here and turn that into u, because check this out. I'm going to take the derivative on both sides. So if this is what u is, then cosine of x is equal to du over dx, and then I'm going to multiply both sides by dx, and I'm going to move that dx differential to the other side right here, so that cosine of x dx is equal to du. So du, the differential for u, is equal to cosine of x dx. So as far as pieces go, this thing right here is du. This part right here is u. And then the part that I didn't use up has to be f. So this right here has to be f. So it looks like e to the u times, go back to blue, du. So this integral here is equal to this integral here under this transformation. Let's go ahead and do that. The antiderivative, the particular antiderivative with constant 0 of e to the u is e to the u. I've got plus c here. And now u is equal to sine of x. So this is e to the sine x plus c. And you can always check your work on these problems. If I take the derivative of this expression, derivative of e to the is e to the. So e to the sine of x, and then times the derivative of the inside. Sine, derivative of sine is cosine. So I get my original function back. Okay. So I wanted to make another adjustment to what I've written right here, in the sense that I wanted to add bounds of integration to this problem. So let's integrate this function, say from 1 to 3. So one of the things that I want to do as I do this transformation right here is I'm going to be really particular about labeling my bounds. That's from x equals 1 to x equals 3. So it would be wrong of me to carry, this is wrong. What I'm going to write down here is wrong, right? Because I've got 1, 3. I'm going to write down 1, 3. And that's wrong because this is x, right? But my variable here is u. So either, right, and I'm gonna, when I have the definite integral here, I'm going to take my antiderivative and I'm going to take the difference of the evaluation at these two places. So I'm going to do e to the sine of x evaluated from e to the u evaluated from. So this is where I'm going to have my evaluated from bar, lower bound. Look, x equals 1, x equals 3. X equals 1, x equals 3. So this one's good to go because x matches with x. This one's not good to go because, like, I have u. I don't have x. I have u. So either, if I want the actual number, either I've got to put in, the x's into this thing right here and then evaluate. So this is going to be equal to e to the sine of 3 minus e to the sine of 1. And that doesn't simplify any further. Or I need to put in, transform this right here so I don't have x's, but I have u's. So how do I do that? Let's do a little bit of side work down here. So if u is equal, u equals sine of x, then u at 1 is equal to sine of 1. So when x equals 1, u equals sine of 1. So as far as bounds of integration go, this transforms into sine of 1. And now I'm going to explicitly put my variable name right there. That's what u equals, right? Here this one's x, but the variable is u. Here the bound is u, and the variable is u, because I have e to the u du. And then my upstairs one is u equals, nope, sine of 3. I don't know why I started row coding. Sine of 3. Okay, so this thing right here is the same as this thing right here. It's just that now the variables match. So I got e to the sine of 3 minus e to the sine of 1, and I better get the exact same thing no matter how I do it. So if I take out these kind of ill-formed x's right here, I don't really like them because they don't match the e to the u, and I replace that with u equals sine of 3, u equals sine of 1, now I don't have to do this final substitution step. I can just do it right here. And that I better get the same number is equal to e to the sine of 3 minus e to the sine of 1, which is exactly the same thing I got as I passed through that thing. So you have a couple of choices when doing problems like this. Either you can not transform and take this code path here, or you can transform and then you can get this one right here, which prevents you having to do the substitution to get the final function. You can just leave it in terms of u. But either way, I think that the addition of labels for like what variable it is that we're evaluating is the thing that really helps with this problem, and seeing that there's a clash. If we were to just leave 3 here, we'd get e to the 3 minus e to the 1, which is not the same thing as this. So pay attention to those bounds of integration when doing your u-substitution problems. I think that's just about what I wanted to say for this particular video. So thank you very much for watching, and I hope you have a lovely day.